Hello, everyone, and welcome to today's webinar, Histology Hacks for Cryosectioning. I am Kaylee Bach of LabRoots, and I'll be your moderator for today's event. Today's educational web seminar is presented by LabRoots and brought to you by Leica Biosystems. To learn more, visit leicabiosystems.com. We encourage you to participate today by submitting any questions you may have during the presentation. To do so, simply type them into the Ask a Question box and click Submit. We'll answer as many questions as we have time for at the end of the presentation. Also, if you experience any technical difficulties, you can utilize this Q&A box and we will assist you directly. With that, I'd like to now welcome our speaker. Joining us today is Dr. Marla Rivera-Oliver, Sales Specialist at Leica Biosystems. For a complete biography on our speaker, please visit the Presenter tab at the top left of your screen. Dr. Rivera-Oliver, thank you so much for joining us. You may now begin your presentation.
Thank you for the presentation and welcome to the Histology Hacks in Cryosectioning webinar. I am Dr. Marla Rivera-Oliver, and I am very excited to share today some tips and tricks I've learned during my 10 years of experience working on basic and translational research. I am based in the Dallas, Texas area of the United States, and in my current role, I support customers from North Texas and Oklahoma. I completed a bachelor's in biology from the Inter-American University of Puerto Rico and a doctoral degree in neurobiology from the University of Puerto Rico. I specialize in the spinal cord injury field and honed my skills in cryosectioning, imaging, and in vivo electrophysiology. Then I moved into a postdoctoral position at the Center for Discovery and Innovation of the City University of New York, where I grew my imaging, histology, and behavioral neuroscience expertise. Before joining Leica Biosystems, I joined the Leica Microsystems team as an account manager for microscopy. I supported the entire microscopy portfolio from compound to confocal and electron microscopy. Since my bachelor's degree, the histology field has always been fascinating for me, where I had the opportunity to do my first tissue staining. Then, during my doctorate studies, I had the chance to do a lot of histology and immunohistochemistry, which led me to publish a great article on spinal membrane receptors. And just to provide some context, here are some beautiful images from Puerto Rico, New York, and Texas for reference on my locations. During our session, I will provide you with some great cryosectioning hacks I discovered while working in the spinal cord injury and locomotion laboratory in Puerto Rico and help generate the quality data needed to publish this paper. I worked mainly with mice and rat brain and spinal cord tissues to understand how the intrinsic mechanism of action of the spinal network affected locomotion or the ability to walk under certain circumstances like injury, alcohol exposure, and even caffeine. To understand the physiology of the spinal network, I perform electrophysiology studies. To understand the anatomy and cell-to-cell interactions, I perform immunohistochemistry and other assays on previously sectioned tissue from the cryostat and the vibratom. The cryostat was key to achieving the thickness and quality of the tissue I needed and preserving its antigenicity. Cryosectioning was the best solution as it was a fast and reliable way to get a tissue ready for staining, and the imaging quality was superior to any other technique I tried. During my learning process, I did a lot of troubleshooting with cryosectioning, like working with uneven tissue and coiling sections. The hacks we will discuss today have the potential for universal applications within any field that uses cryosection, as they are foundations of good practices. I hope you find inspiration and my talk provides value to your research project. So let's jump right in. During this session, we will be covering the following learning objectives. You will be able to identify 3 ways automation improves cryosectioning techniques. You will be able to name Three things essential to obtain reproducible, high-quality sections with cryosectioning. And you will be able to name two histology hacks that can improve cryosectioning. A bit of housekeeping. There will be time for questions and answering at the closing of the presentation. Please feel free to add your questions to the chat box, and we will answer as many as we have time for following this talk. Any questions we do not get to today will be forwarded to me by lab groups for later follow-up. In addition, please see my bio section for more information about me. So with that said, let's start with the main question. What is cryosectioning? Cryosectioning, also called the frozen section procedure, was first described by Dr. Lewis B. Wilson in 1905, the chief of pathology at Mayo Clinic. Dr. Wilson was an expert at microscope-based research and a pioneer in visualizing diseased tissues. Shortly after arriving at the Mayo Clinic, Dr. Will Mayo itself said to him, "I wish you pathologists will find a way to tell us surgeons whether a growth is cancer or not while the patient is still on the table." Dr. Will was frustrated that it involved one operation in getting a tissue specimen, days to determine if it was malignant, anxiety for the patient who had to wait for answers, and a second operation if lab results showed the patient had cancer. Dr. Wilson wanted to create a technique that offered rapid diagnosis of cancerous tumors and masses. Because there was no fast way to provide a cancer diagnosis at the time, he invented cryosectioning. He was able to freeze, cut, stain, and give a diagnosis to surgeons within 5 minutes, oftentimes as quick as 2 minutes. Cryosectioning is widely used in modern science to perform microscopic analysis of numerous tissues with as many applications. The translational science field has embraced the technique to visualize fine details in cells. Let's talk about how that happened. In 1920, the Spencer Automatic Freezing Microtome 880 arrived. The microtome is like that used by Dr. Wilson, although this particular model dates from 1920. But you can see how this cryosectioning technique gained popularity and new inventions arose. Currently, we have a wide variety of options available, from manual to automated cryosectioning. Several labs have developed specialized techniques for different fields to enable a faster workflow and a high-quality throughput. But even though there are many techniques for cryosectioning, they still all must confer the same goal: reproducibility. And with cryosectioning, reproducibility could be a challenging task. There are at least three main factors that contribute to reproducibility. For me, those are rate of freezing, temperature, and cryopreservation. The freezing rate is when the expansion of the water content by freezing stretches and penetrates cell membranes. Slow freezing promotes ice crystal formation and thus expansion. Note that the freezing rate, not the end temperature, is critical at first. Fast freezing depends on several factors: the percentage of the total surface in contact with the cold source, the volume of water, the starting temperature of the water in the specimen, and how cold the source is. Ideally, the cold source is at an extremely cold temperature over -80 degrees Celsius and arranged to contact all surfaces. Panel A shows the formation of ice crystals, a byproduct of a slow rate of freezing. Temperature. Temperature plays a big part in forming different types of ice that can affect tissue and ultimately how it is sectioned. For example, quick frozen or vitreous or amorphous ice is formed below -130 degrees Celsius. This type of ice is semi-stable, forms hexagonal crystals, and is the most common crystalline structure found on Earth. At above minus 130 degrees Celsius, amorphous ice begins to restructure as cubic ice, which gradually expands by result of low temperature and pressure, and will potentially change the morphology of your tissue. Understanding the type of ice formation at different temperatures will help you understand why it's important to section your specimen below 131 degrees Celsius. Sectioning should be performed as soon as possible after biopsy or dissection and should begin as soon as the tissue is warm enough to cut. So remember, we would like to cut the tissue when it is on the vitreous or amorphous state, not cubic. Tissue should never be left overnight or for long periods in the cryostat, even if there is no defrost cycle, as the conversion from vitreous to cubic ice will begin. Crystals will expand the ice and damage cells. The 6 critical steps in cryosectioning are fixation and cryoprotection, specimen preparation, sample freezing and positioning, sectioning, staining and cover slipping, and finally, imaging. I will now discuss each of these steps in more detail. Fixation. Fixation is optional, but should be performed whenever it's possible to prevent autolysis. The sample can be fixed before or after sectioning. The purpose of fixation is to preserve tissues permanently in a lifelike state as possible. Therefore, a variety of fixatives are available for use depending on the tissue and features to be demonstrated. For example, aldehydes, mercuriols, alcohols, oxidizing agents, and picrates. In my personal experience, I have always fixed my tissues with some form of aldehyde. These examples illustrate the value of tissue fixation. On the left panel, you can see an example of a bronchial-alveolar carcinoma with 15 seconds dying time using no fixation, and the arrows indicate where the cellular structure preservation is lost. In contrast, on the right panel, the same type of tissue was immediately fixed with 95% ETOH, a form of alcohol. In this case, the arrows notate preserved tissue morphology, easily visualizing cellular membrane and nuclei. Cryoprotection is optional but very well adopted into the research field. The sucrose solution protects the tissue and makes it less buoyant, so the tissue gains molecular weight and becomes easier to cut. The sucrose solution step for cryoprotection is very common in the research lab. Step number 2, specimen preparation. Immediately before cutting, samples should be grossed or trimmed with a razor blade. Avoid crushing artifacts by gently but firmly securing the specimen while cutting. This enables easy mounting onto the cutting device. A smaller size is preferred as it can be frozen faster than a larger size. In preparing a frozen section, thickness is not as critical as in paraffin processing. It could be 1 centimeter or a little more. If you like more information on grossing, we have great resources available on our website. Please make sure to read Steps to Better Grossing in our knowledge pathway for more details. Step number 3, sample freezing and positioning. Specimens for frozen section can be prepared in a variety of ways. They can be frozen in a cryogen mixture such as isopentane cooled by dry ice, liquid nitrogen, or placed onto a thin layer of cryo compound on a specimen holder that is placed on the freezing shelf, or a large cooled metal block placed inside the cryo chamber. The aim is to freeze the specimen as fast as possible to eliminate ice crystal formation or what is commonly called freeze artifacts. My preferred method has always been to freeze this liquid nitrogen as it provides a fast and even freeze on the sample. For the positioning of the tissue on the cryostat, the most critical edge of the tissue should be perpendicular or diagonal to the blade, and not the first or the last aspect of the tissue to meet the blade. Frozen sections are less stable than paraffin or resin sections, which we won't cover in detail in this webinar, but provide superior preservation and antigenicity and therefore better detection of antigens by microscopy. Step number 4, sectioning. I prefer to section tissue at minus 20 degrees Celsius and thaw mount sections on slides. Slides may be dry on a slide warmer at 37 to 40 degrees Celsius for a few minutes, and tissue sections should be stored at minus 70 degrees Celsius until use. Step number 5, staining and cover slipping. Staining and cover slipping can be performed manually or automated. This will depend on the needs of the laboratory and the volume of tissue. Staining protocols are based on user preferences, and each lab has its own stain combinations. Some labs work strictly with hematoxylin and eosine stains, whereas others can use a wide variety of immunohistochemistry and in situ hybridization labels. Some labs will specialize in electron microscopy. There are certainly a variety of imaging needs, techniques, and combinations available. These protocols may be done manually, which will require much more time and effort, or become automated, which will help the staff, but more importantly, research, as it have the potential to decrease variability in results. Most, if not all, researchers who want to understand where a protein of interest is localized in a cell or tissue usually choose a fluorescent microscopy technique. Compound fluorescent or confocal microscopes are good examples. Using cryosectioning for immunohistochemistry and fluorescent in situ hybridization, we allow for tissue with better antigenicity, make your cutting much faster, and will create beautiful thin sections, even monolayers, that will provide the level of resolution needed at the imaging state. On this image, panel A shows the results of a poorly preserved tissue, which will lead to poor antigenicity. As a result, it can be challenging to identify or quantify data from the tissue section. Panel B shows a well-preserved tissue that conserves cell morphology and antigenicity. We will talk in more detail about imaging later in the presentation. The common goal to strive toward is good quality in tissue preservation. One way to help the preservation of tissue for imaging is using automated cryosectioning. Here I propose 3 pillars for practicing automated cryosectioning. Those 3 pillars are speed, accuracy, and safety. Speed, in physics, means the time rate at which an object moves along a path. In cryosectioning, it means the time rate at which the specimen is moving along the path of the blade or knife, which will be translated into how many sections you will be able to cut in a certain amount of time. Automated cryosectioning can allow for high-quality, faster sectioning. Accuracy. As the cryostat has a pre-established speed rate, each section will be cut at the exact same rate, producing the same accuracy per section. And safety. Safety is important for the user and the tissue. Safety protections may prevent any user accidents with the blade, and it is safe for the tissue as it will be cut with the highest precision, diminishing tissue loss. But what key differences does an automated cryostat have compared to the manual instrument? The three of the main differences are a foot switch versus a wheel for sectioning, which have an automated wheel with turn velocity per rotation, motorized handwheel versus manual handwheel, which increase precision on blade movement. The motorized handwheel will also free both hands to manipulate sections. And the preset counter. So don't worry about the number of sections or trimmings levels already completed when following complex sectioning patterns. Section counter and section thickness totalizer does that automatically for you. Automation means using mechanization instead of a manual or hands-on process. In cryosectioning, automation can consistently strive towards removing variability and improving consistency in cutting and riveting of your specimen. For example, on a manual cryostat, the user sets the parameters and manually cuts, one by one, each section while collecting them on a slide. In comparison, the user selects the parameters and collects sections on automated cryostat, but the cryostat oversees cutting your specimen. Reproducibility and accuracy are key for accurate quantitative and qualitative results under the microscope. Imaging is a world of possibilities. Those possibilities will depend on tissue quality. One way to proceed with imaging is to trace the fluorescently tagged protein while it moves through the cell in real time, which we call in vivo imaging and which we won't discuss in this webinar. However, another strategy is to permeabilize chemically fixed cells or tissues and treat them with antibodies bearing a fluorescent compound. Just to mention a few common fluorescent proteins: GFP, DAPI, Olexofluor, mCherry, and others. These techniques include immunohistochemistry, fluorescent in situ hybridization, and enzymatic degradation. And honestly, the first step for successful fluorescent protein detection is having good tissue preservation. This image illustrates well-preserved tissue under fluorescent light microscopy on panel A, having a higher level of detail under the confocal microscope on panel B, and the highest level of detail achieved under the electron microscope on panel C. None of the tissue morphology and antigenicity will have been preserved if the sectioning protocol had not been perfectly created for the tissue needs. So with that being said, do you know if you have the correct protocol for your tissue? How can you understand what is happening when your results are not as expected? I also had those questions, and I will now share several histology hacks that help me understand what was behind those undesirable results and how to overcome those challenges while cryosectioning. So my hack number one is to pay attention to your fixation protocol. Bad fixation will mean bad results. Whenever you are using a fixation protocol, the fixation time for cells or tissue should last at least 6 to 8 hours, independent on how thick the sample is. This time frame will allow for the covalent bonds to form and maintain the morphology of the tissue over time. For animal tissue, it is preferable to apply the whole body perfusion technique when available, as it will ensure proper fixation of all tissues. There are different approaches for fixation. The most commonly researched are 4% formaldehyde for fluorescent light microscopy or a glutaraldehyde solution for electron microscopy. Other techniques have been introduced to the field, like high-pressure freezing, which is a very interesting fixation protocol, but I have not tried it myself. And then we cannot forget the sucrose solution that I like to include as part of my fixation discussion, because after fixation, the specimen should be placed in a sucrose solution to cryoprotect your tissue during the freezing process, and prevent the loss of morphology and antigenicity. On panel A, we can see well-fixed tissue showing good nuclear and cytoplasmic morphology with minimal shrinkage, showing clearly defined basement membranes and cell margins. In contrast, on panel B, we have an example of poorly fixed tissue showing inferior nuclear and cytoplasmic morphology with excessive shrinkage and poorly defined cell margins. Note the evacuation and fragmentation of both nucleus and cytoplasm of cells of the distal tubule and retraction of the glomerulus due to shrinkage. Let's now move to the cryosectioning hack number 2. Move from fresh to freeze tissue in a smart way. Freeze a tissue sample up to 2 centimeters in diameter. Thicker samples won't freeze evenly and will collaborate with loss of antigenicity. Remember, preserving antigenicity and tissue morphology is our common goal. Freezing the tissue should be a quick process using isopentane or liquid nitrogen, which is the most common, to prevent ice crystal formation, which will change morphological shape. Cryosectioning hack number 3. The right temperature will save a lot of trouble when cryosectioning. I am talking about your instrument, your room, and even your floor temperature. The temperature in the cryostat should be set for your type of sample, usually around 120 degrees Celsius. If the temperature is too low, the block will be too rigid, and the sections won't be smooth and thin. If the temperature is too high, it won't achieve proper riveting. Keep the cryostat door closed as much as possible to avoid temperature fluctuations. Pay attention to the room temperature, which is usually around 68 to 72 degrees Celsius, but low humidity is required. In humid regions like the Caribbean or West United States, we often find dehumidifiers in cryosectioning rooms. Room doors should be closed to avoid temperature fluctuations, and the cryostat should not be placed close to the window, air vent, or a place where sunlight can potentially change the instrument's temperature. In summary, avoid as many temperature and humidity fluctuations as possible. Hack number 4. Use the right tools to achieve the best results. The use of char slides will help with the section adhesion of sites. Use new blades each time you sit to cut. If the blade is dull, it won't cut thin and smooth sheets of tissue. Please remember to use a trimming blade and replace it with a new blade once closer to the specimen. You don't want to make your blade dull before starting to section your specimen. Ensure the specimen and blade are tightened securely and set to the desired temperature. You will also need to use brushes to help while collecting your sections and to keep your working area clean. Soft brushes should be used at all times, and one should try to avoid touching the sections with the brush. Brushes can also help prevent the sections rolling while transferring to the slide. And hack number 5, proper slide storage. You may need to revisit your slides. Store them right. If fixation has been done correctly, your slides will remain intact for several months or even years. Temperature plays a huge role in proper tissue storage. The finalized slides can be stored for months at 4 degrees Celsius in a dark place such as a lab fridge, or stored for more extended periods in an ultra-low temperature freezer, preferably at minus 20 degrees Celsius in a dark slide box. Just remember, keep them stored in a low humidity freezer at a constant temperature and with no light. Another tip is also an add-on to the cryostat called the CryoJane. The CryoJane transfer tape is a method for cryosectioning that makes it easy to produce high-quality, frozen sections from difficult tissues. The CryoJane uses slides coated with an adhesive to help sections stick on the slide instead of the typical used brush. In addition, it can be used with most cryostats. This system can provide sections as thin as 2 microns with excellent quality characteristics such as being intact, wrinkle-free, and good adhesion to the microscope slide. It works by laying a piece of tape to the trimmed tissue block, and a section is cut as captured on the tape, which is then transferred to the adhesive-coated slide. There are several videos on YouTube showing how CryoJane has been used. Type CryoJane on the search bar and you will find the videos. Now that we have discussed several hacks and tips about cryosectioning, I believe it is time to compare how these hacks will impact your cryosectioning quality. Here is a beautiful example of what can be achieved with the CryoJane device by Pinsky et al. The method is also suitable for large brains such as rats and monkeys. Workflow steps are explained on panel A. On panel B, from the Allen Atlas, there are the most common sources of damage, as of folded areas, those solid black arrows, in A, B, and C, torn sections, arrowheads as in C, and sections with missing areas, dotted arrows in D. Those common damages can be corrected by the use of this transfer tape technique. The use of the CryoJane can help decrease tissue damage due to section collection. In the same study from Dr. Spinsky, we show here thumbnail images of serial sections cut from a perfused mouse brain in 3 standard sectioning planes. Selected rows of serial sections cut in the coronal, top, sagittal, middle, and horizontal, bottom planes. Sections were collected using the tape transfer method processed for nasal stain, cover slip, and image. In all cases, the sections appear of consistently high quality. This is another example from the same study. Histochemical panel A and B, immunohistochemical staining in panel C through H, and the use of tape transfer to section rat and macaque tissue is shown in panel I and J. Low magnification views of coronal sections from mouse brains reacted for myelin galase silver stain technique, tyrosine hydroxylase, and Wisteria floribunda lectin, showing high antigenicity. For each image, the arrow points to the region shown at higher magnification in B, E, and F. Tissue with native fluorescent expression is shown in G for a mouse brain expressing credit-dependent GFP in GAT2 cells. Coronal sections of rat and monkey brains collected by this transfer method are shown in I and J. All sections are 20 micrometers thick. So today we have covered several topics of cryosectioning in research. We talk about what is cryosectioning, the 3 ways automation helps in cryosectioning, the 5 steps of the cryosectioning workflow, hacks for better cryosectioning, and 2 bonus hacks and additional tips. This brings my presentation to the end. Thank you for attending, and I will be happy to answer any questions.
All right. Well, thank you so much, Dr. Rivera-Oliver, for your informative presentation. To our audience, before we get started on your questions, we have some questions for you. On the bottom of your screen, you will see a survey with 2 questions there. Please take a moment to submit your answers. All right, and as you're doing that, we will now continue to begin with the live Q&A portion of the webinar. So if you have a question that you'd like to ask, please do so now. Just click on the Ask a Question box located on the far left of your screen, and we'll answer as many of your questions as we have time for. All right, now let's get started. We've already got some great questions coming in here. And the first question that I have for you, Dr. Rivera-Oliver, is there a preferred method for tissue preparation to obtaining quality results?
That is a great question. There is no universal protocol for cryosectioning. Each tissue has its own characteristics, and each research project has its own needs. So for me, a good starting point will be finding a peer-reviewed paper or article that uses a cryosectioning protocol on your specific tissue type and for a similar application. And then, there are labs in science that are, for the most part, open to share protocols and even allow shadowing experiences. That could be another option. Or another option will be to see if your institution has any histology or imaging core facilities. Usually the staff at core facilities are very knowledgeable on sectioning protocols and could be able to assist in the process. The research field nourishes a very collaborative environment, and you may find support at your own institution as well.
Great, thank you. All right, another question here. Is there a preferred method for slide storage?
Yes, the finalized slides can be stored for months at 4 degrees Celsius in a dark place, such as a lab fridge, or stored for more extended periods of time in an ultra-low temperature freezer, preferably at 20 degrees Celsius or a dark slide box.
Wonderful, thank you. All right. Moving on, we have another question here that asks, can you share some additional insights on why cryosectioning helps antigenicity?
Yes, so cryosectioning helps antigenicity because by preserving tissue morphology, it is preserving the membrane proteins that are targets for upstream staining protocols. Cryosectioning a tissue that has not been fixed previously reduces steps on your staining protocol, as an antigen retrieval process is not necessary. And so antigen retrieval is an approach used to reduce or eliminate chemical modifications due to fixation.
Great, thank you. And again, we're getting some great questions in here from our audience, so we'll continue. This next question I have for you asks, our lab currently uses a manual cryostat, and I struggle to get good sections on a constant basis. Can automation help me with that?
It can be a solution for good sections if your pre-sectioning protocol, temperature, and humidity are set right. Automation can help on providing constant reproducible sections and have the potential to make sectioning faster.
Great. All right. Now, can you suggest protocols for antigenicity?
I will suggest finding a cryosectioning paper for your field of study and utilize the method section to locate the right protocol. There's plenty of cryosectioning papers in different fields. You will probably find a scientific paper that can help you or point you out into the right lab to have a conversation with. Or you can also contact your local application specialist for troubleshooting.
Wonderful. Thank you. Now, what should you do if your cryostat is cutting thick and thin, but everything seems tight?
So that is a difficult question to answer. There could be many variables, but I will start by checking the room and cryostat chamber temperature. And if that doesn't resolve the issue, I will just also try to change the blade on the blade holder and see if that makes it better. And if none of them works, I will advise to reach out to your application specialist for additional troubleshooting assistance.
Fantastic. Thank you. All right. Another question here. Could you provide tricks for collecting the cut slices at a cryostat? I have experience with a UC7 Ultra Microtome.
Yeah, that's a great question. I will say that the best way to collect tissue from the cryostat will be to collect them directly into the slide. try avoiding using a brush as we usually use for microtomy. This tissue is not embedded on paraffin, and it can be harmed by the use of a brush. So try to just collect this straight to a charge slide that will help with the tissue adhesion.
Great, thank you. All right, next question here. Is a storage at -80 also good or even bad?
It is good. I think -80 storage will be perfect if you're trying to store the tissue for long term. So that's what I use myself when I was storing tissue once I was done with my imaging, and I have no issues.
Great. All right, now what can I do about the bubbles while sectioning?
That's actually probably an issue with the freezing of the tissue. You'll probably have to check once you submerge your tissue onto the OCT or the freezing mounting solution that you have no bubbles before freezing the tissue. So you're going to have to check on that before freezing.
Great, thank you. All right, well, looks like that's all the time that we have for today. So this will conclude our session. I want to thank you again, Dr. Rivera-Oliver, for your time today and your important research. We would also like to thank LabRoots and our sponsor, Leica Microsystems, for underwriting today's educational webcast. Before we go, I'd like to thank the audience for joining us today and for their interesting questions. Questions we did not have time for today, and those submitted during the on-demand period will be addressed by our speaker via the contact information you provided at the time of registration. This webcast can be viewed on demand, and LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. So until next time, take care, everyone. Goodbye.